Among all the weighted residual method, we have seen that Galerkin method is the most powerful method whose results are much close to that of the exact results. Now let us see, and in fact that is why the Galerkin method is mostly used in the finite element method. Now let us see if there is any scope in improving this Galerkin method. We have here this differential equation, and if you look at this equation carefully, you can come to the point that the residual here r will be equal to minus d square u by dx square minus u plus x square. So here the residual has the order of 2 because the highest differentiation here is d square u by dx square. So here the order is 2. Now if the order is 2, then this demands a starting trial solution of minimum second degree polynomial, because anything less than that will vanish. So if I want to assume an approximate trial solution, the minimum degree should be 2, and in that case it will be a naught plus a1 x plus a2 x square. And let me remind you, this is the minimum requirement, so anything less than this will not work. And suppose say this equation was of say fourth order, then here the requirement would have been of two more variables, or say up to the degree 4, that would have been a cube a3x cube plus a4x raised to 4 if this was say of fourth order. Hence the demand on the starting trial solution totally depends on the order of the differential equation. So we need to find if there is any method by which we can reduce the demand on the starting trial solution. And to that the answer is very simple. What we can do is, we know that the actual definition of weighted residual method is weighting function multiplied by residual, integration of this over the domain must be equal to 0. Now in this case, even before finding what is weight or carrying out this or substituting this trial function in this, what we can do is, I can just write the expression of this residual, that is minus d square u by dx square minus u plus x square dx equal to 0, and then first carry out the integration by part. And if I do that, if I carry out the integration by part, it will reduce the order of this derivative. And for carrying out this integration by part, we know that integral of u into v is equal to u integral of v minus derivative of u, and then again integral of v. So this is the formula for integration by part. And if I had say here u into derivative of v, then this would have been u multiplied by v minus integral of derivative of u multiplied by v. And then further, if I had say u multiplied by double derivative of v, then this would have been u into derivative of v minus integral of derivative of u multiplied by derivative of v. So this is what we will be using it here in this case. And then if I use this here, so let me first multiply this weighting function. Let me first multiply this weighting function with each of these elements. So this will be wi multiplied by d square u. Let me write this d square u by dx square as u double dash minus weighting function multiplied by u plus this weighting function multiplied by x square dx, and this should be equal to 0. So further, I need to carry out this integration by part only on this term, because here there is no order of differentiation. This is just the u term. So really what is bothering us is this term, that is the second derivative of u with respect to x. So if I just do the integration by part on this term, even before substituting any trial function in this, so by this formula, that is integration by part, I can just write this term as I can just write this term as, and in this case let me put substitute the domain also. The domain, our domain goes from 0 to 1, and if I now carry out the integration by parts here, this will give me u, that is w. Here our u is wi and v is u double dash. V double dash is u double dash. So in that case I will have wi multiplied by u dash, limit goes from 0 to 1, and then minus integration of derivative of derivative of this weighting function multiplied by u dash. Again the integration goes from 0 to 1, and this term will remain as it is, minus this will become dx, and this will become integration of 0 to 1 wiu dx plus integration of 0 to 1 wi x square dx equal to 0. So what we have done here is, just by simple integrating, by simple integration, that is integrating this in parts, we have been able to, we have managed to reduce the order of this order of this differential equation. And now because of that, the demand on the starting trial solution has been reduced. So now in place of this, quadratic polynomial, we can even go for a linear polynomial, and that should also help us in solving this problem. Sorry, not here, but I can just substitute this here, because this is u dash is nothing but du by dx, and this trial function is sufficient for this. So this makes it possible to even use the linear solution if desired. So this integration by parts allows us to even use the linear solution. And let me tell you, this is very important in finite element method, since many problems will be modeled, or many elements will be developed using this linear assumed solution, because that makes whole process is much simpler rather than going for this quadratic or cubic polynomial. So this step of integration by parts is very important in FEM, because large class of elements will be based on linear assumed solution. So this is very important in FEM. Now once we do this, then our process is very simple. So I can, for this weighted residual method, so I am assuming now our trial function as this: u is equal to a naught plus a1x is our trial function. But we know that at this point we cannot substitute it in this equation. This is now our new equation after integration by part, but we know that the trial function cannot be substituted now at this moment in this, is because we need to make sure that it satisfies the boundary condition, and especially the essential boundary condition. Now if you just look at this boundary condition, we know that this is essential boundary condition, whereas this is natural boundary condition, but we need to take care of only essential boundary condition at this stage. And if I do that, the essential boundary condition tells us that u at x equal to 0 is 0, which gives us a naught as 0. Therefore our admissible trial solution will become u is equal to a1x. So this will be our admissible trial solution. From here I can very well find the weighting function wi, that is, since here there is only one variable, the wi will be equal to w1, which will be nothing but du by da1, and that will be equal to x. So from here we get that w1 at x equal to 1 will be 1, right? Because at x equal to 1 w1 will be 1, and w1 at x equal to 0 will be 0. And these boundary terms are very much required here to take care of this first term. After integrating this by part, the first term will have the boundary terms. So the first term will always have the boundary terms, and that is why this step becomes now the extra step to check the value of this weighting function at the boundaries, at x equal to 1 and at x equal to 0, or whatever is the boundary in the given problem. We'll have to always check now the value of weighting function at those boundaries. So this weight 1 at x equal to 1 becomes 1, and this weighting function at x equal to 0 becomes 0. Now let us see what happens to this to u So the natural boundary condition tells us that u dash at x equal to 1, u dash at x equal to 1 is 1. U dash at x equal to 1 is 1. So these are all the boundary terms which we have. These are all the boundary terms which we have. And then if I substitute this in this equation, I can get it as w1 u dash at x equal to 1 minus w1 u dash at x equal to 0, after simplifying this term at x equal to 1 and at x equal to 0, minus integration of 0 to 1 w1 dash. I have here w1 dash, and then I also have here u dash dx minus 0 to 1. Then I have here w1 u dx plus 0 to 1 w1 x square dx equal to 0. Now one more very important point that we need to understand is that I cannot do any further integration after this. You might say that since we had done the integration once, I have been able to reduce the uh, order of this u, or order of this differential equation, or order of this residual. So why not to integrate it one more time and further reduce this, so that we even go the demand on this trial function is even reduced. But what will happen in that case is, if you may observe here carefully, although we have been able to manage the order of this term, order of the residual, but the order on the weighting function has increased, because earlier there was no derivative here of weighting function, but now the order of this weighting function has been increased. So what happens in modified Galerkin method is, although we reduce the order of weight of the residual, but we in that process we managed to increase the order of the weighting function. So let me make here a point that any a and y, any further integration by part, any further integration by parts will start increase the order of derivatives on weighting function wi, and therefore there is no advantage in integrating by parts any further. So if we integrate this term by part any further, in that case will be able to increase the order of the weighting function, and that will not give us any advantage as such. That will not give us any advantage as such, and that is why there is no point in further integrating this term by parts. So that this point is very important. We have to note down this point, that after certain limit we just cannot go on carrying out the integration by part, because although we will be able to manage to reduce the order of the derivatives on residual, but in the same process we will also increase the order of derivative on weighting function, and that will not be of much benefit to us. So this is the equation which we get now. This is the equation which we get. And then if I substitute this, so at weight 1 at x equal to 1 is 1, and u dash at x equal to 1 is also 1. So this was given to us. This is what we have found out from here. So this basically becomes 1 into 1 is 1, minus weighting function at x equal to 0 is 0. So irrespective of what is u dash at x equal to 0, which is not given to us, but irrespective of that, since the weighting function at x equal to 0 is 0, this term will become 0. And then minus here the first derivative of this weighting function. From here we get that the first derivative of weighting function will be nothing but 1. So I need to substitute here just this term as 1, and u dash, from here we get du by dx as a1. So I just need to substitute this as a1. then minus 0 to 1. We know that weighting function 1 is nothing but x, and this will become a1 times x dx, and this will become 0 to 1. Again, this is w1 is x, and this x square term is as it is, so this will become x cubed dx is equal to 0. Please see here that this only here the first term after the boundary terms, the first term will have the first derivative of weighting function, but all other terms will have just the pure weighting function without any derivative. So in both these terms we have substituted this w as it is, but only in this first term after this boundary terms, here we need to substitute the derivative of weighting function. So please be careful with this. So this becomes 1, whereas these two terms becomes x, and these are of course the boundary terms which we have found out. So if I carry out this now integration, if I carry out all this integration, I will get this as minus 3 by 4 plus 2 times a1 by 3 is equal to 0, which tells me that a1 is 9 by 8. Now if I substitute this in this function, I will get u as 9 by 8 times 9 by 8 times x. Let me write that again. U is equal to 9 by 8 times x. So this is the approximate solution of this problem. This is the approximate solution of this problem by considering just the linear trial function. We have just managed to take the linear trial function for this second order derivative equation. We have just managed to solve this by taking the linear trial function, and we have got this as the solution, whereas the exact solution was given as 180 by 139x, 180 by 139x minus 21 by 139 x square, and this was our exact solution. This looks to be far away. This exact solution looks to be far away from the approximate solution. But if I just plot these two equation solutions, this is the approximate and this is the exact solution. If I plot them, so this is our approximate solution and this is our exact solution. In orange is the exact solution, and in green is the approximate solution. If I plot them in the domain of 0 to 1, I get this kind of plot. And then of course there is a variation, there is some difference between the approximate and exact solution. But if you consider the quadratic trial function, of course the solution will improve. We know that in any approximate method, if we increase the degree of polynomial, the degree of assumed trial solution then the solution improves. We know this already, that if we go on increasing the degree of assumed trial function, the solution will improve. It will tend to more closer towards the exact solution. But this was the problem to demonstrate what exactly modified Galerkin method means. So again, to revise, modified Galerkin method takes care of the demand of the trial solution on the residual. If the residual is of say second order or say fourth order, what we can do is, even before substituting this admissible trial solution in this, we can just carry out the integration by part only on this term, on the term which has the highest derivative. And if I do that, what happens is we get one boundary term, and then we get the second term wherein we have managed to decrease the order of residual, but we have also increased the order of weighting function, and therefore we just cannot go on integrating further by parts, because although we will manage to reduce the order of residual, we will increase the order of weighting function, and therefore after certain number of steps we need to stop. And then if we substitute, what we see is the demand on the trial function reduces. Exactly, that is what happened here. We managed to solve this problem by using trial function which had only a linear solution. And then we saw the normal process of substituting this weighting function and the trial function, and we carried out the integration and we managed to get the solution. Then, considering the simplicity of this trial solution, the result are not that disappointing. But of course the solution is not that bad. However, there is significant error in the first, there will be some error in the derivatives. If I take the derivative of this function, and if I take the derivative of this function, and if I try to plot it here, I'll get some significant difference. So that is fine, because this is generally the case with most of the approximate solutions, because the derivative never matches well. But of course, again, if I choose the approximate solution of say higher order, then I can somewhat come over the first derivatives of it.